Yeah, so today I'm going to be talking about something that's a little bit different to the other talks in this session, but hopefully you'll find it interesting and useful. It's on the subgrid parameterization of eddies, mean field, and topographic interactions in simulations of the Antarctic Circumpolar Current. I would say representative, but yet idealized. I'd like to acknowledge the contributions of my co-authors, Professor Jorgen Friedrichsen and Professor Terence O'Kane, and also acknowledge funding from the CSIRO Artificial Intelligence for Missions program. Okay, the motivation for my work is to address resolution dependence and the numerical simulation of nonlinear systems, specifically geophysical fluid dynamics today. As we all know, it's not possible to resolve all the scales of motion for these flows on a computational grid, which is why we resolve only the large scales and we have to parameterize the unresolved subgrid scale interactions. The typical approach, as done in the classical Smagorinsky schemes and others, is to start off with a physical hypothesis of how proposed subgrid interactions behave, and then develop a subgrid model from that. We do the opposite. We calculate the subgrid coefficients from a high resolution reference direct numerical simulation, from which we can then make physical interpretations concerning the direction of energy transfers. This has been a successful approach in previous studies with application to two-level quasi-geostrophic atmospheres, oceans, and 386 level turbulent channel flows. Today, we're going to be revisiting the ocean case, specifically an Antarctic circumpolar-like flow with realistic bathymetry. We're going to use a spectral code to simulate the flow today. It's a two-level quasi-geostrophic potential vorticity equation solver. Just to recall everybody, the reduced potential vorticity is given by the surface normal vorticity plus a layer coupling coefficient multiplied by the difference between the stream function of both levels. And it's this layer coupling coefficient that effectively sets the central wave number where baroclinic instability is dominant. So we solve for Q on two levels, levels 1 and 2, for the total and zonal wave numbers N and M, and this is done over the complete wave number set denoted by bold T. The ODE governing the evolution of Q is given by the Coriolis force plus a drag force parameterizing unresolved boundary layer processes. We also nudge to a target climate, and this target climate has been extracted from high resolution ocean GCM run that's been done previously. And also the important nonlinear term capturing the interaction between eddies and the interactions between the eddies and the topography. And it's really only this term that we need to, this is the key term that we need to address in any subgrid modeling studies, because it's only the nonlinear interactions that can transfer energy between scales. All the other linear terms are irrelevant in that context. And then we have a bare dissipation, which parameterizes the scales that are not resolved in our highest resolution model. So to maybe illustrate the flow configuration that we're going to look at today, whilst it is a global ocean configuration, it's if you like, an aquaplanet, and we're primarily interested in the Southern Ocean, specifically the ACC region. So we only have bathymetry defined within this ACC region, and that climate that we're nudging toward is also only defined in this region. Some of the key parameters are the dominant wave number. The wave number at which baroclinic instability is centered, dominant, is here at Kr. This is effectively set by that FL parameter on the previous slide. T is the maximum resolution in our high resolution reference DNS. So what you see here is the kinetic energy spectra of the ocean flow. So we're going to be truncating this system to two specific resolutions, one in which baroclinic instability is not resolved, so one where we're going to be chopping this spectrum in this region, and we're going to calculate the coefficients such that a lower resolution coarse-grained simulation can reproduce the statistics within the large scales, and another in which baroclinic instability is explicitly resolved, so on the right-hand side of this KR. Okay, so the first step before we do that, we need to create a database by which we can learn these coefficients. This is a pictorial representation of the nonlinear interactions in the triangular wave number plane. So all of these colored triangles within this black triangle, these represent the nonlinear triadic interactions. So this first column is our reference high resolution direct numerical simulation solving for the PDE. So this is at time step 0. The DNS then evolves to time step 1 all the way through to time step n. The way that we extract the subgrid tendency, the first step is to calculate the resolve component. So at each field of the DNS, we take a copy of it, take it over here. We zero all of the scales that we would ideally not want to resolve in our lower resolution version. So all of these high wave numbers, smaller scales, they are all set to 0. We then use this now truncated or coarse-grained system as an initial condition. We take one time step with this initial condition, and the only triadic interactions that survive are those that have nodes that are fully contained within the large scales. All of the other triadic interactions that have at least one node in the small scales have been zeroed out. So then after that, now we've calculated the resolve tendency associated with this field. We then go back to the DNS, take the next time step, take a copy of that, coarse grain it in the same way, or zero out the Fourier coefficients in the small scales, take a time step with this as an initial condition. Now we've got the resolve tendency of the next field. And with this, we repeat this process for the whole time series. Now, the difference between the complete tendency and the resolve tendency is by definition the subgrid tendency. So that's where we get back all of these subgrid interactions. Importantly, because we're only taking one time step with the model, this red triangle out here is irrelevant for the subgrid modeling procedure. Because over one time step, if all of the nodes are contained within, all the nodes in the interaction are contained within the subgrid scales, they cannot influence the resolved ones. So they're irrelevant from the subgrid modeling perspective. So the only interactions that we're really concerned with are these cross terms that have at least one node in either the resolved or the subgrid scales. So now that we've generated this database of time evolving subgrid tendencies and time resolving fields, in this most primitive form, one could consider the subgrid modeling task as being how to relate subgrid tendency to the field within the resolved scales, resolved large scales. So before we do that, we can further decompose these subgrid tendencies into each of its fundamental classes of interactions. So the first class are the eddy-eddy interactions. So these are interactions between subgrid eddies and resolved eddies. The orange in this slide means subgrid, black means resolved. The eddy meanfield interactions. So these are interactions between the subgrid eddies and the resolved meanfield, and also the subgrid meanfield and the resolved eddies. Eddy topographic interactions. These are interactions between subgrid eddies and the resolved topography, and also subgrid topography and resolved eddies. And the meanfield Jacobian, which are interactions between the subgrid and resolved components of the meanfields and the topography. So mathematically, the way this looks, we've got our complete subgrid tendency over here, and that's given by our eddy-eddy interactions, which are by definition the fluctuating component of our subgrid tendency, fluctuating in time. And that we model using this stochastic formulation. And then all of these other terms, these sum together to give you the time invariant component, or the time average subgrid tendency. And these three components, one of which is proportional to the mean field, they're the eddy mean field interactions. Another component is proportional to the topography, they're the eddy topographic interactions. And the final component is the mean field Jacobian, which we can actually explicitly calculate from the DNS itself. So this functional form hasn't been invented. It's as a result of the quasi-diagonal direct interaction approximation. It's a formal renormalization closure of quadratically nonlinear systems. Strictly speaking, each of these terms, each of these operators in the closure are slowly varying and have non-Markovian integral representations. In our data-driven approach, we assume that they're time invariant, and then we can sample them from the this database that we've previously calculated. I just want to spend a little bit more time on the decomposition of these interactions, because I think it's important and hopefully informative. This is kind of a tree diagram that I've come up with to illustrate how each of these things get split. So we have the complete tendency. So this is from the DNS, of which we decompose that using our procedure to get the resolve tendency component. and the subgrid component. So this resolved component is the bit that's resolved in the by the coarse grid, and the subgrid tendency is the part that needs to be parameterized. And the subgrid tendency itself has a time fluctuating component, which we parameterize using this linear stochastic formulation, which are by definition the eddy-eddy interactions. And the mean component is then decomposed into these three terms: the eddy meanfield, eddy topographic, and meanfield Jacobian. Each of these interactions can be associated with specific terms in the non-linear component of the ODE that I showed you originally. So when you add all of these terms together, some of them cancel out, like this one cancels out with this one, and then you return the full non-linear term in the DNS. So now that we have our mean subgrid, our subgrid tendency, and our resolved field, this is the procedure by which we go to calculate the parameter coefficients that govern the eddy-eddy term. The key point here is that we're exploiting the property of turbulence, if you like, that subgrid interactions are local in wave number space. This is not true in grid point space. So what I mean by that, I can write a subgrid model for a particular wave number pair or a particular scale for which the subgrid tendency at that scale is a function of the resolved field at only that scale. You can't do that in grid point space. It's not true to say the subgrid tendency at a particular point in space is dependent on the field and all the other field variables at only that point in space. Because of spatial correlations, it's also dependent on the surrounding points. If you think about how an ocean model works, you might have Laplacian operators or biharmonic operators that are parameterizing horizontal mixing. In the calculation of the stencils for the Laplacian and biharmonic operators, they're drawing in points surrounding the point that you're trying to calculate the subgrid tendency for. And in doing so, they're approximating this non-local property. So anyway, we're doing it per wave number pair, and then I would argue it's more more in line with the nature of turbulence. So to do that, we define bold Q. So this is for a particular wave number pair, because we have a two-level model here. We've got the top level and the bottom level. And what we're going to do, we're going to calculate a unique dissipation operator for every wave number pair. We have this approximate deterministic model. I'm going to illustrate how we do it for the deterministic case purely just because it's easier to explain. And then we'll get to the stochastic case in time. So we have the fluctuating component of the subgrid tendency. It's a two-element column vector. That's equal to this 2x2 matrix multiplied by another two-element column vector. So because we know this and we know this, we just post-multiply this expression by the complex conjugate of Q hat, or the fluctuating resolved field, and then time average both sides. So we have a 2x2 covariance matrix on this side, and a 2x2 cross covariance matrix on this side, post multiply by the inverse of the covariance matrix, and that gives us DNet. And we do that over and over again for every wave number pair. So the key point here is that there are no tuning parameters. These coefficients are just what the data tells you it should be. The stochastic approach, there's a few extra steps, but the moral of the story is the drain dissipation operator and the variance of the stochastic backscatter force are all calculated from the data itself with no tuning parameters. Okay, move on. So this is kind of what these coefficients look like. Recall, we're starting off with a high resolution DNS with 504 wave numbers. This is what the stochastic formulation of the subgrid tendency looks like. We've got a two-element column vector here, given is equal to this 2x2 matrix multiplied by another two-element column vector plus the stochastic force. Here I'm illustrating just the upper diagonal term of this drain dissipation operator. So you can see these coefficients are weakly dependent on M, but strongly dependent on N. And the way you would interpret these coefficients, positive values means that energy needs to be taken out of the system, or this operator will act to take energy out of the system. And negative values will inject energy into the system. So you can infer the energy transfers from the sign of these coefficients. As you approach the truncation scale, so the smallest scale still resolved within your Corson model, have the strongest interactions with the subgrid because purely they're more similar in size. So that's quantified here by these coefficients having larger amplitudes. So we do this at the two resolutions. This top one is representative of baroclinic instability not being explicitly resolved. And here at TR's 378, this is baroclinic instability is explicitly resolved. We can compress this information by averaging in the M direction. That just allows us to look at all of the coefficients on one plot. You'll see the diagonal elements for both the lower resolution and higher resolution truncations. They increase steeply as n increases, so as you're approaching the smallest resolved scales. The higher truncations also have weaker off-diagonal elements of this matrix. So it's saying that the subgrid tendency of this particular level is not only dependent on only that wave number pair, it's really only dependent on that level. That's not true for the case in which baroclinic instability is not explicitly resolved. The subgrid tendency at a particular level is dependent on the field on that level, but also the field on the other vertical level. So that's how we calculate the Eddy-Eddy interactions. The next part of the cookbook, if you like, is to decompose the mean subgrid tendency. So if you recall, the mean component, or the time invariant part, is given by the meanfield Jacobian plus the Eddy meanfield interactions plus the Eddy topographic interactions. So this process is all done spectrally. I've just converted them into maps, physical space maps after the fact to hopefully be more illustrative. This is what the mean subgrid tendency looks like in total, in its entirety. So this is the map that should be added to your time derivative every instant in time to correct for the missing subgrid eddies, the missing subgrid topography, the missing subgrid mean field. And we can calculate the meanfield Jacobian component of this by using the mean field as an initial condition, taking one time step in the model, and then doing the same with the Coulson mean field. And you can see in this space, in terms of the barotropic meridional acceleration, the meanfield Jacobian is a negligible part. And the Eddy meanfield and Eddy topographic components appear to be equal and opposite, but there are some regions in which the symmetry is broken. Might also note that it is dependent which space you look at. So here we're looking at it in meridional accelerations, but if you were to look at a time derivative of vorticity, these terms are not as symmetric. And we do the same again for the higher resolution case. Just in the interest of time, I might move on. So the final step to check that all of this is appropriate, all of these coefficients are reasonable. We take the Eddy parameterization and all of the components of the mean subgrid tendency, and we put it back into the Coulson simulation. So this red dashed line, that's our high resolution DNS. And the black line is if we just simply truncate it and apply no additional subgrid modeling at all, and you get, as you would expect, ridiculous results. But if you add in our stochastic variant of the Eddy interactions and all of the mean subgrid tendency components, or the deterministic one, it largely corrects for the missing scales. We've also run experiments where we've turned the mean subgrid tendency off completely, and the solution does degrade very slightly. So the moral of the story is that the Eddy interactions are clearly the dominant case. Just wanted to note the top spectra is the real energy level. I've just offset all the other ones for clarity. These top two are for the case in which baroclinic instability is not explicitly resolved, and these bottom ones are for where it is. I think I'm running out of time, so I might just skip this and go to the physical maps. We've also compared the mean zonal velocity fields between the DNS and all of the LES variants. So this is what the the barotropic component of the zonal velocity from the DNS. This is the difference between the DNS barotropic zonal velocity field and that of the LES with no subgrid modeling at all. And you can see there's a whole bunch of biases that are introduced. If you use either the stochastic or deterministic variants of the Eddy-Eddy interactions with either the mean subgrid tendency included or not, that all reproduces the mean field quite well. So in conclusion, For the first time, our general data-driven subgrid parameterization approach has been applied to an oceanic flow with topography. And we've calculated coefficients representing the Eddy-Eddy interactions, Eddy topographic, Eddy meanfield, and also the meanfield Jacobian. LES or coarsened resolution versions adopting these coefficients have statistics in very good agreement with the DNS across all scales, recognizing also that there are no tuning parameters in this approach. Fortunately for ocean model development, the Eddy-Eddy interactions are the dominant ones. And I say fortunately because these coefficients governing these interactions are self-similar. And we have, in our previous work, developed a set of scaling laws that allows you to determine what the appropriate properties of the Eddy-Eddy dissipation is without having to go through this data-driven process. And finally, I'd like to add maybe a general point that subgrid parameterizations, be them data-driven or physically motivated, can be reasonably expected to address missing physical interactions. They're not the solution for excessive dissipation in ocean models or atmosphere models or anything due to the numerical methods employed. And I'll leave it there. Thank you.